So I'm going to speak about MOSAiC, and MOSAiC is the Multidisciplinary Drifting Observatory for the study of Arctic climate. And this is very much a large collaborative effort, an international collaborative effort. So myself and Klaus Detlef are kind of the drivers of this activity, but there's a lot of different teams involved. We've had a science plan writing team working together. This is an international and interdisciplinary team for quite a while. There's been a few proposals so far to get platforms, to get some measurements involved. And then from the U.S. side, we're starting to put together the pieces for putting out some proposals to different agencies into the future. So there's a lot of people involved, and there's more than are even listed on this first slide. So MOSAiC is targeting the sea ice in the Arctic, the mosaic of ice flows that are pictured here, and importantly, the mosaic of processes that are occurring within that sea ice system in the Arctic. Importantly, these are interdisciplinary processes relating the sea ice to the atmosphere, to the ocean, to the ecosystem. So really targeting those interactions. I'll probably cruise through some of these early motivational slides because I think we all probably get the big picture here. We understand that the Arctic's in a fairly rapid transition with a lot of change, especially to the cryosphere. The important point here, though, is, we pose the question, do we know why these transitions are happening, and do we know how they are at the process level? And I would argue that we don't have a sufficient understanding of the how of these changes. And of course, there are a lot of implications to change, and I don't want to belabor this again. The first one, though, I would say is pretty important, and it's that we do lack that system and process level understanding of the change. So without really understanding the change at that level, then it challenges us to project where the system is going into the future. And then, of course, the change has a lot of implications as far as implications for things like connections with lower latitude weather, resource development in the region, et cetera. I think we all appreciate these. Certainly with our, if we're involved in IARPIC, we understand these. So a view of the Arctic system from the energy budget perspective might look something like this, with a lot of movement of energy in the system. These arrows are representing flow of energy. We've assigned some numbers here. These numbers are highly uncertain. Some of them are big, some are small. And ultimately, it's these fluxes of energy through the system that are going to influence things like the sea ice mass budget. And recently, Kwok and Untersteiner suggested that this decadal decline we've seen in the sea ice can be explained by something on the order of 1 watt per meter squared excess energy in the system. And so that 1 watt is really small relative to these generally much larger fluxes moving around the system. And also, importantly, the uncertainty of these fluxes. I mean, a lot of these numbers have been derived from individual campaigns at a certain location or a certain time, or some attempt at spatial integrated values from satellites. But we have huge uncertainties, and there's huge spatial variability in these flux terms that are moving through the system. So to really get at an understanding of decadal transitions in the Arctic, we need to better constrain a lot of these fluxes in the system. And unfortunately, our models are not very good at doing a lot of that. So this is one example of looking at broadband radiated fluxes in the short wave and in the long wave at the surface. And this is evaluating a whole host of regional models, regional climate models, against observations from Shupe, which is out over the sea ice, over the course of a full year. And what we see in these plots here, I don't know if, do people see my pointer moving around the screen there?
Yes.
Okay, very good. So we see here a short wave and long wave radiation, and in the top panels we see clear sky. So we're evaluating these models, the clear sky models, against radiative measurements at the surface, and we see indeed a lot of spread, which is expected because maybe a given model won't get the absolute variability of the synoptic situation. But importantly, at these times, we see that the kind of mean intermodal mean is something around 0 under these clear sky conditions. But then if we look at cloudy skies, we see a lot more spread, but we also see, importantly, a bias. And these biases are really significant. So for the short wave, we're talking 25 watts per meter squared, long wave about 10 watts per meter squared, with a lot more variability. And so these numbers are very large relative to the small fluxes or imbalances needed to impart significant change in the system. And there are similar challenges in other aspects of modeling the Arctic climate system. This is just a comparison of sea surface salinity among a number of global models looking down at the Arctic domain. And the main point here is that we just see these major inconsistencies among models. We don't really have a consistent understanding of something as important as sea surface salinity. So this suggests larger problems with things like ocean